Why a proof is a set.
No, a proof is an element of a type of proofs, and the type of proofs is a set. Okay, so proofs are terms. Terms live in types. The types whose term inhabitants are proofs correspond to propositions. In this case, instances of a relation. Apologies for just diving in.
No. Honestly, everyone should feel free to dive in at any point. This is exactly a tutorial. So open group discussion session.
This is the first time. Well, this is the second type definition that we've seen here, right? After the natural numbers.
Yeah, we also defined equality last week, which is actually very similar. If we remember, we looked at the definition of equality, which was, well, it's parameterized by some sort of set, but it's A to. So this is very similar. This was an equality, but equality was between anything of arbitrary types, and you gave it two arbitrary elements, and then it returned you a type of proofs. But type of, yes. James has got it much more sorted in the exact words in the type of 90. Returns you a set. But less than or equal to is purely we insist that you give us two natural numbers.
Right.
So how can we prove that two natural numbers are less than or equal to each other? Well, again, we do it by induction, which is what PLFA was telling us. So we have the cases are somewhat analogous to the zero and suck cases in the natural numbers. So the first case, which is called in the standard library and in PLFA, we can always prove for any natural number is greater than or equal to 0. So we have a name of a new proof, a new constructor, and it says, so for start off, we're just going to go for all n, and we're going to make it explicit. I'll come back to it. For all n, 0 is less than or equal to n. Okay. So
I had maybe a quick question about this, because I mean, I think I also saw you doing this, because the problem was I was running into when I was trying to do this is that whenever I wanted to do this less than or equal to and then followed by an n, it would change it into a negated less than or equal to. So
okay.
So yeah, so if you're typing /leq len, then indeed you get it's short for not less than or equal to. So what I have learned to do by muscle memory that I don't even think about anymore is that you press LE space n, and the space always gets you out of the Unicode.
And you need the space anyway, because if
you do need the
type
space.
LE and then n, this is just a name.
So
but that is a name that's given there, which is my point.
Yeah, so if you're trying to
the name of this term is
here, for instance, on the letter here, right? If you type LEN, then you'll get less than or equal to rather than typing. So yeah, so you type space, and then you have to go back and press N again.
Okay, but there's no reason to get out of this having to put a space and then going back again.
There's definitely ways.
So let's copy. The way to do it is to see if there is any shortcut, is that you copy the character, and then somewhere there's a file on the Agda repo, which I'm sure you can bring up in Emacs somehow, but I haven't learned how, that has the list of the character codes plus all of them. So you can see, and you can usually type them in multiple different ways. So you can see here that I've searched for this less than or equal to sign. You can get it by a LEQ. You can also get it by /less than equals. So that might be a way of doing it if you want to do, and less than equals. Oh no, it does have less than, it has an n afterwards. So that wouldn't work. So no, in conclusion that you're stuck with it. I'm sorry, space, and then n.
Can you press escape?
Can you press escape? That might be possible. Less than or equal to escape n. Ah, no, because escape is a special character in Emacs. So it does get you out of it, but then expecting.
Possibly Control G or something. There's probably some way to escape.
Oh, yeah. Okay, less than equal to Control G N.
But that's basically just Emacs thing that will hopefully drop you out of the input mode. So that's Emacs specific, right?
Yeah. Okay, so let's try and use this. So we can prove that, for instance, that 0 is less than or equal to 3. And because we've declared this as misfix notation, we can provide arguments that actually look nice. We can, the type of this, yeah, so this is a type, and this is the name, and then we have to give a proof that this type is inhabited. We have to give an element of this type for it. And well, we can ask Agda using control refine, do you know of any things that you can fit in here? And it says yes. And we have a z less than equal to n. And it needs an argument, and that's the n. And if we go control A, it will tell us that it's 3. So I'm not sure we touched on, did we touch on explicit versus implicit arguments in detail?
Probably due to the fact that we looked at like a big
quality, yeah. So it's a bit of a pain, right? Having to provide this argument explicitly every single time. Whenever you want to go z less than equal to, when you want to prove 0 is less than equal to a natural number. So you can make different arguments in Agda can either be, there's 3 different types. There's explicit arguments, which you always have to give. There are implicit arguments that Agda will try and infer from the type. So implicit arguments are used curly braces around them. And if we do this, then it will just pick it up automatically. It says, I know, it looks at the type of the expression, you know that it's a proof of 0 less than or equal to 3. You've given it z less than or equal to n. So it's saying, okay, I've got 0 on the left-hand side, so that's fine. I've got n on the right-hand side, and I need to pick an n such that this term will give me 0 less than or equal to 3, and it can pick the right n. So implicit arguments get you a long way in writing readable Agda code. There's a third type of argument called instance arguments, which we won't touch on very much. Basically, whereas implicit arguments Agda will try and reconstruct it from the type information immediately available. Instance arguments is Agda actually has to do a search through the space and tries to do something much more advanced and clever, and actually does a much bigger inference procedure and can do much more magic on its own. But for the moment, we'll just cover implicit arguments. Okay, so we can now prove that any number is less than or equal to 0. Sorry, greater than or equal to 0. So this next inductive step, right, is that if we can prove that m is less than or equal to n, then we can prove that m plus 1 is less than or equal to n plus 1. So sup of m is less than or equal to n, sup of m. And indeed, so what does that say? Well, it says that for all m and n, if m is less than or equal to n, then we can prove that sup of m is less than or equal to sup of n. So the successor, yeah, if m is less than or equal to n, then the successor of m is less than or equal to the successor of n. And using that, we can, for instance, prove that 1 is less than or equal to 4, for example. 4. Well, it's not a 0 case, so we're going to have to use successor. So we can refine it, and then we get exactly our goal proof is then 1 is less than or equal to 3, which we can either provide z less than or equal to n directly, or we could feed in 0 less than or equal to 3. Yes. Anybody have any questions about this? Is everyone happy with the idea that what you would think of as this relation can be constructed in exactly the same way as classically you can think of as data in other more traditional programming languages?
And is everyone happy that the definition Matthew's just developed is actually different from the one in the book?
Oh,
No, in a good way.
in a good way.
In a good way. So in the book, they supply the additional type information to the arguments n and mn.
Yeah, so they have that.
But notice, you don't have to, because you've already announced your intentions in the type signature for the relation. So any arguments that are in position for that relation are not going to type check unless they're nats.
So Agda is, yes, inferring that M&M must be naturals.
Martin,
Yeah.
okay, what would happen if you check for 1 less equal to 5?
So 1 less than equal to 5. Interestingly, it's
Check.
so it looks syntactically like the same proof, right? Which is kind of weird. So why has the proof not changed syntactically? But what has changed underneath the hood that is not evident here?
That's a good question. It is a different proof.
It is a different proof. This is a different proof, right? Because it's 1 less than equal to 5 versus 1 less equal to 4.
No, it's not. It's the same truth because your inductance was starting. and your inductance-
Oh, it is a different proof.
It's a different proof because Z-lec N there, it has a different type than it had previously.
Yeah, so it has the same structure. You're right. The proof has the same structure,
But the truth term is the same.
but
No,
actually,
it's not.
the proof term is not.
Make these explicit. Make these
Yeah, so
explicit.
If you
All
want
of
to
them.
give explicit arguments, if you want to give these implicit arguments explicitly,
Yeah.
you can give
Yeah,
them
types.
using brackets.
Yeah.
These the same brackets that you use to mark them explicitly. So if we insert them here, and there's 2 here, right? This proof that 1 is less than or equal to 5. Well, the first one, S is less than or equal to S, the suck is less than or equal to suck. What do we have? Well, it's got to be, M has got to be 0 and N has got to be 4 for this.
I mean, Agda knows.
Agda knows. Yep, we can fill it in. Ooh, ooh. Oh, that's got it. It's annoying that it doesn't. And then we can fill it in. So this is the actual proof that Agda is constructing underneath. If we then change it to 1 less than or equal to 4 again, this no longer type checks, right? Because it's got to be 3 and 3 here. Right? So the proof term, syntactically the proof is the same, but the implicits that Agda is filling in underneath the hood are different. That's an excellent question, Margot. And yeah, it's
So there's a couple more issues, I suppose. One is, how do we know that what we've defined is actually a less than or equal relation of natural numbers?
yes.
And I mean, it's something that basically you have to take care of or think about whenever you're doing interactive theorem proving, that what you're writing, what you're formalizing is what you mean to formalize. And this is a topic with some history and a lot has been said about this. But in general, we sort of have to convince ourselves that this is what we intend to, what we mean by
And indeed, this is where most of the bugs that you will find in your development. Interestingly, the types, if you write the types right, your actual computation is usually bug 3. The much more common thing is that you've actually written what it means to be correct down wrong. And hopefully that means if you've written what it means to be correct down wrong, hopefully that means that your algorithm won't work. But sometimes it does. And very occasionally you run into trouble where you've got a bug in your spec, basically. And those are quite subtle and hard to spot. But better than having a bug in your, at least it's one step up from bugging program. So how would you check that this relationship, how would you increase your confidence that less than or equal to was actually encoding the less than or equal to relationship over natural numbers? What are some things that you could prove about it?
Yeah, I suppose.
So the obvious things, for example, that you might want to prove is that it's reflexive.
Yeah.
Right? that for any natural number x, for any natural number n is less than or equal to n. So we can prove, so for all n is less than or equal to n. And this is relatively easy to prove. So it's got takes one argument n in. We case split on what n is. If n is 0, what does Agda want us to supply? Well, it wants us to supply the proof that 0 is less equal to 0. That's easy. As I said, less equal to n. And if we've got suc n, if n is equal to suc n, well, that's relatively easy too, because that's exactly our s less equal to s case. So we can press refine, s less equal to s, and in fact, and then we've got to prove n is less equal to n. Well, we can just apply we can apply induction, right? We can recurse on s equal to REFL. Indeed, if you press auto, Agda will fill that in for you. So if you then want to prove that 5 is less than 5, you don't have to write out all the s. You don't have to write out all the s. S suc s less equal to s, s equal to s, s equal to s. You can go less than equal to REFL. Let's just check that. And indeed, well, so we can fill in 5, we can ask Agda to fill it in for us, or we can say, we can put underscore there, and again it will infer that it knows what we need to put there.
But notice for this definition, the value of that expression actually is s less than s applied to 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 z less than n.
Yeah, so let us try and I don't know, give it any time. Let us try, so we can ask Agda to normalize what our proof of 5 less equal to 5 is.
That's not going to be an and.
No,
Yeah.
so I'm just asking you to normalize it in the whole.
Oh yeah.
I just want the whole. I just want the whole.
You just needed that. Yeah.
So if we type 5 less than equal to 5 in this whole, and we press Control C, Control N, that asks Agda to fully expand everything that we've given it. And indeed, you can see that the less than equal to REFL proof actually unfolds to exactly the proof that we would have to write manually. So s less than equal to REFL, although it's a proof that
Inductive proof.
but it's an inductive proof that all natural numbers are less than equal to themselves. It is actually doing computation. It is actually constructing the proof term. And that means that you can run, you can run proofs in exactly the same way as you can run, addition or run. Okay. Any questions at this stage? Any more questions? How far have we skipped ahead?
A little bit.
A little bit. Indeed, they're talking about implicit arguments, which I think we've covered. Yeah. Okay, precedence. Yes. So.
The other thing you didn't do was, did you do named implicit arguments?
No. Okay. So yeah. So that's a good point. So if you have implicit arguments, explicit arguments are just given by position, right? You have to give them all. So if you've got three explicit arguments, then you just have to give them in order. Bam, bam, bam to the function. Implicit arguments, you might have three, or you might have a sequence of implicit arguments, but you only actually want to give one of them explicitly. So here, for example, is where we've done it. We've given a 0 less than or equal to 3. So suppose we only wanted to give the second argument, n.
We would. The 0 is clear from the structure.
Yes. Yeah. So suppose we only want to give the second argument n. Well, this doesn't work, right? If you just write this is assuming that you're going to give 3 as the m here. So instead, you can give it a name. You can give it, if you say the same name as the argument was originally given, and yes, and you set it equal to 3. Interestingly, although this is a lovely feature, this makes it really painful in terms of backwards compatibility. because interestingly, you might think that these implicit arguments aren't, the names of them don't matter, and that you can change them because they're never, in normal code, they're not actually ever referred to because they're getting implicitly, but actually,
Except
people-
for this place.
it comes in useful in this place, and actually changing your names to implicit arguments will break stuff if people are giving them explicitly. Cool. Precedents. Did we cover precedents in previous weeks? I guess we have new people here, so. So let's import addition from the natural numbers, which we did last time. Is this going to work? Precedents. Yes, it is. Okay. And let's try and, for instance, prove that for all. Well, let's try and come up with an interesting proof. For instance, that for all m and o, if m plus n, sorry, if m is less than or equal to n, then o plus m is less than or equal to n plus o plus n. So modulicity, I guess, plus on the left-hand side. Now, I have written this as you might write this in maths, right? But if I write this, Agda is going to complain. And it's going to complain with a very cryptic error message, sadly. And it says that n should be a sort, but it isn't. Anyone have, can anyone, I would be impressed if anyone can interpret from the error message what's going on. But does anyone have any ideas about what might be going wrong with me writing this? Maybe the error message does come.
It means brackets, so it means precedence and brackets, right?
Yes. So what actually, so addition in previous weeks was set at the precedence of, if we look at addition, where is it? This is the built-in.
It was there.
It was there?
The first input.
Oh yeah, first infix. So it was set at a precedence level of 6. Okay, and it's left associative, so it associates to the left. By default, any misfix operator or infix or prefix operator that you define comes at a default precedence of 20. Okay, which means that we've defined this less than or equal to, and it's at precedence level 20, and plus is at precedence level 6. So what this means is that Agda is, at the moment, trying to bracket it like that. Right? Because it doesn't know where less than or equal to 6 in relationship to plus. It's just saying that it doesn't know that it's less than or equal to in maths, and the convention is, we have to tell it what the convention for this symbol is. So this error is saying, okay, well, we've got something of type set here. The m less than or equal to o is a type set, and we're trying to add it to a natural number, right? And it's saying that, okay, well, you're trying to, trying to add two things together. It's saying that it's doing some sort of casting upwards, and it's saying, okay, I've got a set here. I'd expect these things to be sets as well. I'm a bit confused about where this error message actually comes from.
This is a
Because I would expect it to be the other way around. I would expect it to say, okay, this is a natural number. We've got plus that's doing natural numbers. Oh, hang on, we have something of type set here. I would expect it to say set should be in n, or it should be a set in itself. But I'm not sure if anyone has any bright ideas about why this bracketing produces this error message.
I think the bracketing goes all the way to the right. I think the right bracket is after n.
Does it change anything?
I don't think so. It doesn't change anything. But I don't think it is. I don't think it is, because plus, again, it's another plus. So anyway, so we're going to quietly brush why that particular error message comes up, and instead talk about the solution. So the solution is to set the precedence tell Agda what our precedence of our less than equal to is. And I think the standard one for less than equal to, I'm going to check because I never know. So it needs to be less than equal to 6, basically, in order to say that plus is more tightly binding.
Can't you alternative just put proper brackets?
Huh?
Can't you
So-
alternative just use proper brackets?
Yeah, so if we comment that out, Luca is exactly right. If we instead bracketed like that, Agda would be happy.
We can even check how it bracketed the right hand side.
We can even check.
Well, if you remove the right hand brackets,
Yes.
otherwise it'll be an error.
Yeah, so
it
I
seems
think
that,
I think it was bracketing just the
yeah,
middle.
Mhm.
But we don't want to write brackets everywhere, right? Well, if we can possibly get away with it, and if it's clear and unambiguous to users about what we mean, right?
Yeah.
There's some argument about having brackets if you're using a weird convention, but in such a simple, like, accepted formalization of a basic concept where everyone has that mental model of how the precedent should work. And then now I've given the infix, that works. We used to have lots of problems in the standard library that we kind of ran out of numbers. Precedents used to have to be integers, and we kind of set our precedences all kind of close together when the standard library was first. Luckily, they have introduced you can now have fractional precedences as well. So we now have an infinite number of precedences that we can play with. Not super recommended, but it will get you out of a tight spot if you are ever trying to define an operator between something that's level 4 and level 5. Yes. Okay. So, decidability. Yeah, so we have this notion of what it means to be. We have this notion of what it means for one number to be less than or equal to another, right? But we don't yet have a method for deciding, given two arbitrary numbers, can we, does it hold that one is less than or equal to another? So the decision procedure is separate from the definition of the relation itself. It talks about defining, yes, and so as part of the proof of decidability. So what would decidability look like? It would be a proof. Let's have a look at. So the standard way. So okay, so there's two ways of doing this, right? In a standard programming language, you would have some sort of method that takes two natural numbers and returns a Boolean value, true or false. Is this number less than or equal to the other one? Okay, in Agda, we can do one better. It's perfectly possible to define that function, but we can do one better. We can define a function that takes in two natural numbers and either gives us a proof, constructs us an actual proof of why one is less than or equal to another, or a proof that no such example exists, that type is uninhabited. So does that make sense? So it's stronger in that sense that we can actually give an informative proof. We can give something informative back from our decision procedure, not just a yes/no answer.
In this case, of course, there's not really a difference between the two because there's at most one type of inequality, and at most one term of inequality for any pair of naturals.
Yes and no. So yes, in the sense that there is only one, because the way that we constructed our type, there is only one way, there is only one valid, for every n less than or equal to m, there is only one valid set of constructs, sequence of constructors for constructing that proof. So every one of those types has exactly one element in it. So in that sense, yes, these proofs don't hold any information. On the other hand, for example, if you have a proof that m is less than or equal to n, you can actually compute m minus n from that, right? By looking at how many s less than or equal to s constructors there are in that. So you can actually, the thing that you've returned actually holds computational information that you can then use in further proofs. In a way that true or false, if you just return true or false, you don't have that, you don't have that information available to you in an easily digestible form.
Yeah, so my point was just that if you get true, then you can also easily compute like a canonical term because there is only one.
Yes.
Yeah.
So yeah. So in this case, yeah, that's definitely true. And actually, I mean, this is general design decision that is often, this is an important design point that actually touches upon. If you can construct your proofs, the specification of what you want to prove in such a way that there is only one proof of it, then do so, because that will save you, it will help you a lot later on, particularly when trying to prove things like congruences of functions over proofs. In practical terms, in standard, I mean, it's okay. We in the standard library we call it irrelevant. It says that if a relation is irrelevant, if for every instantiation relation there is only one element in it. And using irrelevance, you can prove that if you have a function that takes in a proof that m is less equal to n, then applying it to two different proofs of that m is less equal to n is always going to result in the same thing. And that is often, and when I say a function, often it's another proof that in turn relies on it. So yes, so if you can try and make your relations only have one inhabitant, then that's also good. Okay, so how do they go about doing this?
Doing what?
Decidability. Oh, so they
Decidability,
don't
not
talk
yet.
about
We
talk
have to
about
skip a
decidability.
couple. We haven't seen a someplace,
We haven't seen a sum type.
and it's a couple chapters before we do. So yeah.
Yeah. Okay. So we'll sorry, apologies. We'll come back to decidability. Apologies. I saw the heading and got all excited.
I think I apologize to the author of this tutorial.
Yeah.
On his
Well.
behalf.
Yeah. It's an important concept. So it's because it's actually how you make decisions. Right? It's actually how you run a program. Like actually do something computational. Okay, so now talks about proving relationships. Some of the relationships.
sorry,
We've already looked at
Well,
reflexibility.
does
I actually have a question about this invertibility because it's
Yes.
Hooray!
because right because I mean it says the obvious thing, which is that right if you have proof that some successor is less than or equal to some other successor, then there's only one possible way that proof can occur, namely by applying s less than equal to s.
Mhm.
But how does it know this? So how does the underlying, how does Agda tell that 0 is not a successor?
That 0 is not a successor.
Yeah.
Okay. Can we look at the definition of natural numbers?
Yeah.
So this is the definition of natural numbers that's there in the first chapter, right? We've looked at it.
Mhm.
And it has two constructors. One is 0, one is successor. And the two constructors are always distinct. So that is for any data type, like in any functional programming language or anything like that, right? The two constructors are distinct always. That makes sense?
So it's,
Yeah, I guess.
it's correct me if someone will shout at me if I'm wrong, but it is syntactic, right? At this level, it's purely saying that suc of m can never be equal. The check that suc of m does not equal 0 is purely syntactic.
Okay.
Yeah, basically, the constructors are injective by definition.
Okay.
Yes.
Yes.
Well, yes, but you have to prove. You often.
Yes, constructors are injected and disjoint by construction.
But okay, but you have to prove, for instance, that for all m and suc of m. Okay, so it is, yeah, yes.
Yeah, but that's an inversion principle, right? Just like the one on the
Yes. Yes.
same
Okay.
principle. Same
It
as
is. It is.
with,
Yeah.
less
It is
than
the
or
same.
equal, right? So yes,
But
you
that's
have to
also,
prove
yeah.
inversion. You don't have to prove the other way around. Well,
Yes, it's injectivity on the. I mean, what I wrote is the classic definition of injective, right? In mathematics.
Yes.
But injectivity of constructors is injectivity on a different level. On the internal level.
So it's a good question, Ezra, and it's good that some of the discussion has been a bit hesitant, because in fact, inversion is the simplest instance of dependently typed pattern matching, and that is the single holy mystery of the subject. So it's good
Yeah.
to be worried about the holy mystery.
So like there's even a question like, why is there even just one case here?
Yep.
There's two cases in the definition of less than or equal. Why is there just one?
So let's have a look. Okay, yeah. So let's try and explore this. So, okay, so we have two implicit arguments m less than n. So let's write them out. Okay.
And proof P. Why not?
And proof P. Yes. So let's have a look at what cases. So let's have a look at what's going on underneath the hood. So as you might imagine, let's pattern match on something that is not dependent, right? To start with, let's just pattern match on m and n, which are just natural numbers, so they're easy to do. So we'll pattern match on them both, and we get the four cases. Okay. So
Gosh, that's new. I didn't know you could do multiple splits now.
oh, I'm glad I can teach you something.
Fabulous. Wow. Okay. No, I learn new things from you every day.
So what would, so now I've got 0, 0. What would P look like? Well, P is a proof that this will be 1 less equal to 1, right?
Yep.
So we can pattern match on P, and it's going to be S less equal to S, and it's going to give us some new proof P that P is less than equal to 0. The 0 is less than equal to 0. So if we pattern match on P again, then we get Z. We know that to be 0 less than N, and we can just go Z less than equal to N. Now, the crucial thing to note here is that no matter what our pattern match on 0, M or N are, that P is always going to be a proof of something in the form suck less than equal to suck.
Yeah,
right?
That's what we said.
Because indeed, that's
right?
what we said at the beginning. Okay, so Agda knows that Agda looks at our definition of less than equal to, and it sees that it's got to produce something of form suck less equal to suck. Okay, so it knows that it can't use this constructor. Z less equal to N. So if we go all the way back to the beginning and pattern match on P, case split on P, it's only going to give us one case for it, because it knows that Z less equal to N can't possibly. And indeed, if we write Z less equal to N here, it's going to give us an error, and it says the case for constructor Z less equal to N is impossible because unification ended with a conflicting equation. 0 is equal to suck of N, which is actually a really good error message.
Yeah.
Well, standard of error messages, active error messages, that's good. So, is there any more magic that you would like to talk about, James, or Philip, about this pattern match on this dependent?
I think the sort of practical understanding, or at least the practical intuition, is that because your data type is dependent, right? The data type of equality proofs it depends on the values of the first two arguments, M and N. If you look at the cases for the pattern match, it will often it can tell you something about the values of M and N, right?
Yeah.
And yeah, sometimes because of how M and N look, some cases will be impossible. And
Yeah, because in the sort of the first split on M&M that you did, you'd run into problems, right? Because you would have some absurd cases there.
No,
No.
no, I don't think we would have absurd cases.
Yes.
because
This can happen, and it's not a problem,
The
really.
third case
Oh, right.
will be observed.
Yes, sorry.
oh yes, sorry, yep.
Oh, that's good. That's great.
Yep.
Could you case
So-
split on P here?
Yeah, so let's see what Agda says when we try and say case split on P. We have a goal that suck M is less than or equal to 0. And it says, okay, well, it's
No, so it will work because, of course, if you can find some term like s less than or equal to s of p,
Yeah.
then of course this will work. But of course, you can't find such a term, but that doesn't matter.
Yes.
Okay, yeah, right.
Right, that's not what I wanted.
Well,
I mean,
Yeah.
okay, so Agda is happy with this case, right? Because it holds, but you would never be able to, if you ran this proof and normalized it, you would never actually be able to hit this case,
yes.
which is an interesting. Yeah. Yeah. But yes, yeah. So what? So for instance, let's try and feed it an invalid proof. So let's say, let's take in 1 is less than or equal to 0, and I don't know, well, for the moment, it doesn't matter what the output type is. So last thing to do. So let's take in a proof of 1 is less than or equal to 0, and then we can pattern match on it. Okay. Agda gives us, interestingly, Agda gives us these two brackets. And this is called the absurd pattern match. And it basically means that this case, Agda has worked out that this case can't possibly hold. And interestingly, it hasn't left us a hole, right? It said that, yes, it hasn't given us a natural number. We haven't given it a natural number to produce.
Or the right hand side. It didn't even leave us with
a place to give a
equality
natural number.
sign, right? It's just.
But this is, so it seems a bit weird, but this is actually consistent, right? Because it says, you have given me something impossible, right? Therefore, this can't possibly ever run. This can't, you
can't get there.
you can't feed in such an argument into this function. And therefore, what this function produces on that argument, well, I don't care. I mean, it doesn't matter what it produces because you can never hit this input case. Does that seem logical or seem scary or? Well, you have, I mean, so if you try and use this lemma, right, then you're going to run into trouble. It's going to warn you when you try and use the lemma because you're going to try and give it something and it's going to say it's not of the right type. So the warning comes when you try and use it. Yeah. Okay, cool. It is now 2 o'clock, so I guess you can leave it there. I hope everyone has a good Christmas for those who aren't going to dinner. Yeah, I think we'll continue.
Do we have an agreement on when we want to meet after New Year's?
Should we take a larger homework?
I mean, the homework, I guess, would be for people who are the people who are actually interested in using Agda, I guess, can have a small play and try and do the very basic steps into what they would like to formalize, and then they can bring. There will undoubtedly be questions. Well, maybe not. Maybe everyone's maybe everyone's imbibed enough Agda that they're now experts in it. But if they then want to bring any questions back to the session in the new year about problems they ran into.
But straight after this bits that we covered comes exercise. Well, there are properties of ordinary relations, which is obvious enough, and then exercises. So should we do? And then I guess there.
Yeah. Alternatively, if people would like to do the exercises, then and again have problems with them or have questions about them, please do bring them back to the next session.
But otherwise, then we want to finish this chapter next time.
Yeah, I mean, I think that we'll keep going through until we hit the
Also, if we're like going too slow or something and boring people, then shout at us.
Yes.
Where will the recording be put?
The recording will be put on the Isaac YouTube channel, which I will. Do you have? There's a link on it on the live seminar page, and it will be up hopefully by the end of this afternoon.
Okay, thanks.
On that note, I will stop recording. Oh, we've got messages in chat. Were they recorded? Oh, yeah, well,
Okay.
okay,
Well,
cool.
Thanks for today.
Yeah,
and,
thank you. Bye.
We'll be meeting sometime in January.
Yeah,
Um,
first half of January probably there'll be. We'll send a message
probably, I
around.
think 14th,
14th maybe. Yes, 14th.
something like that.
14th seems like.
Or, no, 14th is seminar, I think.
No, so
So what- Okay.
What's his name?
send
Just said that he
everyone
can't
else.
make it.
Before everyone goes, there is just one thought for Christmas time. Because Luca has got this autonomous car and is now recruiting insane number of MSc students to work on the autonomous car. It now looks like we're gonna be running some kind of seminars on basics of the autonomous car, because I have no idea what this car is about. So there will be the 6 so MSc students, me, Luca, Yukui, Marco perhaps. So I think we will have it anyway, because we must have it. We must understand at least as much as our students are supposed to understand. So it will be, I don't think we'll schedule this at the same time as these seminars, but if you like, I will just email to everyone present here. It might be the seminar after Agda or same day or different, I don't know. Do you have any ideas when it's best to schedule this, when the autonomous car seminar?
I didn't realize we're doing live ones, like the LinkedIn lecturers, want to do live ones.
We'll probably need to start meeting, for just giving tasks to MSc students. Well, it will be something like reading your previous, taking something and copying.
We can organize some stuff. And
Yeah, okay.
I guess different as well.
Okay, so maybe, yeah, if you're gonna come, this will be the same day. So
Yeah.
maybe let's keep the autonomous car seminars on Friday as well, but maybe substantially spaced, maybe 10 a.m. rather than afternoon or something
Yeah.
like that.
Okay.
Anyway, so if someone wants to learn not just Agda, but also autonomous car, though the connection may not be clear to you.
The normal kids.
Feel free to do it.
And then Matthew next year will do how to do a fire controller and iPad.
Yeah, yeah. Why not? Why not? If I come to the.
Well, yes, I'm trying to switch. I'm trying to switch their improvers. I think when it comes to actually verifying something on the car, but
Well, you have already some control optimization.
oh, it's a toy. I mean, it's on Agda purely because I don't want to have spent 2 months to learning something new to formalize something toy-like. But yes, we're switching plans to switch to something called Kimara, which is a interactive theorem prover that is based on differential logic. So it's based about reasoning about differential equations, which sounds kind of exciting. But yeah, cool. See you guys later.
Bye.
Bye.